Ladies and gentlemen, a warm welcome to today's lecture entitled Plasma's Atmospheric Pressure from Fundamentals to Technological Applications in Materials and Science, which will be given by the researchers of the Laboratory of Innovation of Plasmas from the University of Córdoba. First of all, as a representative of our research team, I extend our heartfelt gratitude to the Quebec Centre for Advanced Materials for affording us the opportunity to present the potential of atmospheric pressure plasmas in materials science during this lecture. Before exploring the fundamental aspects of atmospheric pressure plasma, let me briefly introduce you the University of Córdoba. It is placed in the south of Spain, in a city also named Córdoba, and offers an undergraduate and postgraduate studies. Among teacher activities, the teaching faculties carry out research activities within a research group. In our case, we develop our research program in the Laboratory of Innovation in Plasmas. Who belongs to the Laboratory of Innovation in Plasmas? Well, the group is formed by permanent professor, postdoctoral researcher, and PhD and master students. There are 9 of us, and our research is devoted to specific topics related to atmospheric pressure plasmas. Professor Madero Dolores Calzada is the group leader, who has an extended expertise in the characterization and development of atmospheric pressure microwave plasmas applications. Our research program pursues 2 main research lines. The first one is devoted to basic research of atmospheric pressure microwave plasma, which includes plasma characterization and diagnosis. With this information, we can understand plasma kinetics and study thermodynamic equilibrium degree of plasmas. All this basic knowledge is applied to development of interesting plasma applications such as hydrogen production or the formation of graphene from the composition of a precursor, among others. Therefore, our 2 research lines complement each other. In this lecture, Laboratory of Innovation in Plasma team will try to briefly present how atmospheric pressure plasmas can contribute to the development of amazing materials. For that purpose, this lecture is divided in 3 sections. First block is devoted to the understanding of atmospheric plasma fundamentals, while second and third ones are focused on the use of atmospheric pressure plasma for the treatment and functionalization of surfaces and the synthesis of graphene and plasma modeling for this purpose. Once the outline of today's lecture is being presented, let's start by understanding the fundamentals of atmospheric pressure plasma for materials science.
Good afternoon, everyone, and welcome to the first block of this course, which will be devoted to the fundamentals of atmospheric pressure plasmas. In it, we will begin by briefly discussing the definition and classification of plasmas. After that, the main sources for the generation of atmospheric pressure non-thermal plasmas will be introduced, and to conclude, some applications of atmospheric pressure plasmas will be presented. Essentially, a plasma is an ionized gas. However, there is more in it than the fact of the existence of free charges, electrons and ions, that allows untapping their large potential for applications. The existence of plasma or radiant matter was first identified by Sir William Crookes, and it was a few years later that their nature as ionized gases was acknowledged by Irving Langmuir, who used the term plasma to refer to this radiant matter because its aspect reminded him of blood plasma. Plasma is also often referred to as the 4th state of matter. This derives from the analogy of phase transformation by subsequent additions of energy. Thus, we can transform a solid into a liquid by adding some energy to it, and if we keep adding energy, it will eventually transform into a gas. In this situation, if we keep adding energy to a gas, some of its atoms or molecules will be ionized, leading to the existence of free electrons and ions besides neutral particles, resulting in a plasma. However, not every partially ionized gas can be classified as a plasma. Formally, a plasma is defined as a quasi-neutral gas of charged and neutral particles which exhibits a collective behavior. Quasi-neutrality requires the plasma to be able to balance positively and negatively charged particles locally, it is, within a small volume. The collective behavior requires the plasma to be able to respond as a whole to external or internal electromagnetic perturbations, meaning that long-range interactions must predominate over short-distance interactions. Simplifying this picture a little bit, we can say that a plasma must be large enough and contain a sufficiently large number of free charges to screen both external and internal electromagnetic perturbations within its volume. At the same time, in order to be considered a plasma, electromagnetic interactions must be more important than interactions with neutral particles. Plasmas spontaneously occur in nature both as astrophysical and atmospheric phenomena, such as stars, lightnings, or nebulae. The picture of a burning sun and a much fainter aurora illustrate the fact that plasmas can exist in a wide range of conditions that include not only different gases and pressures, but also covering equally wide temperature scales. This allows tailoring plasma sources in laboratories that cover equally broad temperature scales with very different objectives that range from the treatment of thermosensitive materials using radiofrequency plasma jets or to obtain energy through thermonuclear reactions. Ultimately, this development can be implemented in different technological fields that will be discussed during this presentation, and some of them are even of customary use in everyday life, such as plasma displays or lightning bulbs. However, regardless of the technological field, controlling the composition of the plasma is essential for it to act efficiently in an application, and this depends on its microscopic composition. At a first glance, since it is a partially ionized gas, it is evident that inside we will find ions and electrons. Typically, electrons are the particles that absorb most of the energy of the electromagnetic field used to sustain the plasma and then, through inelastic collisions, produce new ionizations. Consequently, we usually pay attention to the density when studying a plasma. But not all electrons will have enough energy to produce ionizations. Some of them will only have enough energy to produce excited species, both atomic and molecular, or maybe to break the bonds of the molecules, giving rise to highly reactive molecular fragments. Thereafter, these species will be able to participate in reactions with other particles in the plasma or with the substances we put it in contact with. This means that the energy of the particles involved in the different reactions will also play a role in the composition of the plasma and, therefore, in its performance in a given application. This energy is usually represented by the temperature, but what do we mean by temperature when we are in a plasma? Inside a non-ionized gas, particles can exchange kinetic energy through elastic collisions. This establishes an equilibrium that we call Maxwell's equilibrium, in which not all particles will have the same kinetic energy, but which allows us to define the temperature as an statistical average of these energies. It is possible to do something similar with the rest of the possible processes inside a plasma. Thus, the excitation-de-excitation balance, which we call Boltzmann equilibrium, allows us to define an excitation temperature. The ionization recombination equilibrium, which we call Saha equilibrium, allows us to define an ionization temperature. And finally, the radiation equilibrium, which we call Planck equilibrium, allows us to define a radiation temperature. As with the Maxwell equilibrium temperature, all these temperatures represent statistical averages of the energy put into play in the different processes that can take place in a plasma, and they somehow represent the energy available to carry out different processes in our applications. Consequently, it is important to have some knowledge of them. Next question concerning this topic would be if all those temperatures are the same. Luckily for us, the answer is no, and ideally, from a very simplistic point of view, we will need to be able to increase those temperatures according to the application we are interested in. The case where all temperatures defining our plasma are the same is called thermodynamic equilibrium, which takes place when all the characteristic temperatures are equal: kinetic, excitation, ionization, and radiation. It is a rather rare situation in the laboratory. The situation is lost when the emitted radiation is not reabsorbed, giving place to local thermodynamic equilibrium. This allows us to use techniques such as optical emission spectroscopy to characterize our plasmas. Moreover, electrons are much lighter than the rest of the particles in the plasma, and sometimes kinetic energy is not efficiently transferred to heavy particles in elastic collisions. If this happens, two different temperatures are required to describe the Maxwell distributions of electrons and heavy particles separately. If the excitation and ionization kinetics is still controlled by inelastic collisions with the electrons, we call this a two-temperature plasma or non-thermal plasma. This is a relatively common situation in laboratory plasmas and has a great advantage for many applications of plasmas, since we will not be investing energy in heating the gas, but only in the excitation processes generating excited particles and reactive molecular fragments. Besides, since the temperature of heavy particles is what we call gas temperature, it is the temperature we would feel if we touch the plasma, it opens the possibility of treating thermosensitive materials. Further deviations with respect to this last equilibrium situation are also possible, but lie beyond the scope of this talk. Anyway, the applications that will be discussed in the next sections of this lecture will be related to two-temperature plasmas. As we have seen in the previous slides, electrons are the particles that largely control the kinetics of plasmas, and both their density and temperature determine the energy available to carry out processes inside the plasma. So it is reasonable that a first formal classification of plasmas can be made as a function of their electron density and temperature, as it is shown in the left image. In it, we can find both plasmas, those that exist in nature and the artificial ones, and in particular, the area marked in red approximately corresponds to the non-thermal plasmas at atmospheric pressure, which are characterized by electron densities between 10 to the 11th and 10 to the 15th electrons per cubic centimeter, and electron temperatures of the order of thousands and tens of thousands of Kelvin. These electron temperatures ensure the capability of atmospheric pressure non-thermal plasmas to efficiently break the bonds of most molecules or to conduct the chemical modification of the substances or materials in contact with the plasma. In the advanced materials field, synthesis and functionalization, for practical reasons, the plasma classification can be made in terms of the gas temperature instead of electron temperature. The right image shows some examples of devices that work at different temperature ranges from few hundred up to around 15,000 Kelvin. Another practical classification of plasmas is the one that takes into account how the energy required to sustain the plasma is coupled to it. Thus, we can sustain a plasma using an electrostatic field generating a DC discharge or an electromagnetic field. The use of Joule heating based on the production of heat when a current passes through a gas can also successfully be used to sustain a plasma, as in the case of nuclear reactors driven by magnetic confinement. Lasers can also be used to sustain plasmas, as in the case of inertial confinement or laser-induced plasmas. Given the wide range of frequencies on which an electromagnetic field can be generated, plasmas sustained with this kind of field can be subsequently divided into radiofrequency plasmas, those working with frequencies ranging from 1 kHz to 1 GHz, and microwave plasmas, sustained with frequencies ranging from 1 GHz to 100 GHz. Numerous approaches have been developed to sustain plasmas with electromagnetic fields, which is the type of plasma most frequently used in technological and industrial applications. And this can also be classified depending on the way in which the field is coupled to the discharge. In this way, in the case of radiofrequency plasmas, we find inductively coupled plasmas and capacitively coupled plasmas. On the other hand, microwave plasmas can be coupled by resonant structures, surface waves, or direct absorption of the field energy. This latter segment of the classification will be further developed in the next part of this presentation.
In the upcoming section, we will specifically focus into the realm of electromagnetic fed plasmas, exploring how the application of this field shapes the behavior of the system. When subjected to low-frequency excitations, particles of both low and high mass undergo sufficient kinetic energy distribution throughout the system, fostering thermal equilibrium. This equilibrium is particularly attainable under low-pressure conditions. Conversely, when operating at atmospheric pressure, achieving thermal equilibrium becomes notably challenging, even at low frequencies. The fact that equilibrium is hardly reachable in these conditions opens the possibility to work at interesting regimes such as the so-called cold plasmas. The utilization of electromagnetic-fed plasmas at such conditions make them highly compatible with potential industrial applications. Furthermore, there is no need for a vacuum pump, which makes these plasmas even more attractive for implementation in mass production. Even within these atmospheric pressure conditions, the frequency of the energy source significantly influences the system properties. Three distinct regions emerge based on these parameters. At low frequencies, ions exhibit the capability to track electromagnetic field variations, even when their mass is orders of magnitude higher than electrons. As frequencies increase, the systems enter the realm of radio frequencies, where the field varies more rapidly than ions can follow. Electrons, possessing significantly less mass, continue to track these variations. Further escalation of the frequency leads to the microwave region, augmenting the effect observed in the radio frequency domain. Subsequently, we will provide illustrative examples for each of these conditions and engage in discussions regarding the pertinent properties. It is crucial to note that the presented parameters correspond to helium-argon gas inputs, given their prevalence. The versatile nature of these setups render a comprehensive generalization of their properties nearly impossible. Let us start talking about direct current at low frequencies. These systems consist on a cathode, which is where the electrons are emitted, an anode, where electrons land from the cathode, and a plasma gas, which is introduced in the system by the gas injection system. This plasma subgroup is very versatile. Its temperature can vary in a wide range depending on the device used. Among these plasmas, we can find some devices that are widely used. Arc plasma torches, two-electrode discharge, for example, used in the metal industry, corona discharges, which consist on two conductors widely enough separated and with a certain difference of potential, which have a huge number of applications, such as the manufacture of ozone, ionic wind devices, among many others. Finally, we will be talking about the electric barrier discharges in a different slides. The electric barrier discharges devices, from now on DVD devices, are widely used in the industry because of its properties. At first instance, a DVD device consists on two plain parallel metal electrodes. One of them is covered by a dielectric, which can be a material that is wanted to be treated. Furthermore, gas temperatures are relatively low, which is in fact a very useful characteristic when it comes to treatments of thermosensible materials. In addition, streamers that go from one electrode to the other are distributed randomly, which ensures a homogeneous treatment. Diffuse discharges can also be obtained in barrier discharges configuration at atmospheric pressure with a gap width up to several centimeters. In a diffuse configuration, the discharge is spread out over a larger area, typically across the dielectric surface. This is in contrast to filamentary discharge, where the plasma is concentrated in narrow filament-like structures. The diffuse configuration is often characterized by a more uniform distribution of the discharge across the dielectric material, leading to different plasma characteristics compared to filamentary discharges. This configuration is especially useful, for example, for the position of homogeneous thin layers on a desired material. In the realm of radiofrequency regimes, ions and electrons exhibit distinct behavior, as we discussed in the initial slide. Contrary to the conventional cathode-anode configuration, these devices are characterized by electromagnetic excitation featuring frequencies within the radio range. In the classification of plasmas, a pivotal distinction arises between high-power and low-power devices, significantly influencing properties such as gas temperature and, consequently, the potential application of the plasma. Among the high-power devices, inductively coupled plasmas stand out. These plasmas derive their energy input from electric current generated through electromagnetic inductions generated by time-varying magnetic fields. Conversely, low-power devices in the form of microwave-induced plasma involve a radio frequency antenna surrounded by a grounded conductor tube, creating a plasma gas flow. The application of the discharge primarily consists on the application of the reactive species present in the effluent. Finally, the last branch of the classification of electromagnetic fed plasmas at atmospheric pressure is microwave-induced plasmas. The frequency of this electromagnetic field makes ions and electrons enhance its behavior from the previous regime. There are three types of plasma reactor: resonant structures like V-Necker cavity, plasmas contained inside a dielectric tube, and free expanding plasma torches. We will be focusing on the last two classifications in the next slide. Particularly, we will talk about Surfatron and Tiago. In this slide, all the featured devices operate at a frequency of 2.45 GHz, with power inputs ranging from 50 watts to 1 kilowatt. These instruments, designed and generously donated by Professor Michel Moissan of the University of Montreal, are operated in the Laboratory of Innovation in Plasma. The two primary devices under discussion are the Surfatron, which is a relatively isolated system characterized by a quartz tube enveloped by a microwave antenna, emitting radiation in a unidirectional manner. With minimal contact with the surrounding atmosphere, this device is sensitive to small concentrations of gases different from the main plasma gas, as they can induce instability in the discharge. The maximum power input for the Surfatron is restricted to the range of 200 to 300 watts. The Tiago torch, which is a much more powerful device capable of withstanding higher concentration of reactive or precursor gases distinct from the primary plasma gas, is capable of standing power inputs of 50 watts to over 1,000 watts. These apparatus feature a nozzle responsible for supplying plasma gas to the system and directing the electromagnetic field. The Tiago torch, being a more intricate system, presents a higher level of complexity in study due to the increased interaction with the atmosphere, resulting in greater turbulences. The introduction and classification of the different types of plasma at atmospheric pressure have ended. Now, some applications of plasmas will be discussed in the following section.
Now, it's time to talk about the applications of atmospheric pressure plasmas. But first of all, let's see why they are a suitable tool for several applications. Plasmas, in general, provide a highly reactive environment which is suitable for multiple purposes, including the dissociation of molecules. For this reason, plasmas act as a source of reactive species of nitrogen and oxygen, which are known to play a key role in several applications. In addition, plasma technology working at atmospheric pressure is more suitable for its implementation at industrial level, together with the fact that it is a cost-effective, eco-friendly, and reproducible tool. The diversity of plasma sources allows to fully take profit of their features for different purposes, opening a wide range of applications in several fields. Before getting deeper in any specific field, let's have a general perspective of some of the most prominent applications of plasma technology. One of the most everyday applications of plasmas is illumination. High-pressure plasmas are very radiative media, so if they emit in the visible domain, they can be used as light sources. Two kinds of lamps must be considered: electroded lamps, such as the high-pressure mercury lamp, and electrodeless lamps, with increasing interest since they avoid reactions between the electrode and the plasma. Among this type of lamps, sulfur ones stand out. Another important application is chemical analysis. In analytic chemistry, glow discharges and ECP torches are widely used, and also discharges contained in the electric columns at atmospheric pressure, as shown in the figure. There, it is shown a device and method called lateral sample introduction to introduce gaseous samples into a plasma column generated at atmospheric pressure for analytical purposes. In addition, as the plasma is a high chemically reactive media, various products can be synthesized, for example, hydrogen, ozone, or hydrocarbons. The synthesis of ozone is especially interesting due to various applications of this gas in chemical and pharmaceutical industries. Moreover, hydrogen stands out for being a source of green energy. Other long-established applications are nanomaterial synthesis, such as graphene, and surface treatment, including cleaning, etching, and activation. These two topics are going to be later discussed by my colleagues. So now, let's focus on applications of atmospheric pressure plasmas on different fields, starting with industry. Material machining is one of the most important applications of atmospheric pressure plasmas. This kind of application requires high temperatures, so plasma sources such as arc plasma torches or microwave torches are used for this purpose. For welding or cutting by arc plasma, an inert gas sheath is used to avoid contamination from the surrounding media. High-power arc plasmas also suit for their use in metallurgy. The working power can reach several megawatts, and such high energy levels are necessary for extractive metallurgy or melting and purification of metals. Another essential application of plasmas in the industrial field is the coating and functionalization of surfaces. One of the most used techniques for surface coating is plasma spraying. In plasma spraying process, the material to be deposited, typically as a powder, is introduced into the plasma jet emanating from a plasma torch. In the jet, the temperature is on the order of 10,000 Kelvin, so there the material is melted and propelled toward a substrate, where the molten droplets flatten, rapidly solidify, and form a deposit. These coatings can give interesting functionalities to the original surfaces. Another technique to perform surface functionalization is atomic layer deposition. In the past few years, plasma-enhanced atomic layer deposition has obtained a prominent position due to its implementation in high-volume manufacturing and a wide range of plasma atomic layer deposition reactor designs. For performing this method at atmospheric pressure, it stands out the use of surface dielectric barrier discharges. Moving to biomedical field, plasmas find there a wide range of applications due to the generation of active species of oxygen and nitrogen, which react beneficially with organic tissues and biological materials. A good example of it is the plasma-tissue interaction for wounds healing. Plasma devices are also used to treat infective or inflammatory skin diseases like herpes zoster, atopic eczema, acne, athlete's foot, or actinic keratosis. For this purpose, plasma jets are the best investigative plasma source from the physics and biomedical point of view. In this field, it stands out plasma engineering of biomaterials and soft materials. Soft materials are those that can easily be deformed by thermal fluctuation and external forces due to their low shear modulus relative to their bulk modulus. They have stable jet flexible characteristics in a way in between liquids and solid, and are deformable but with a resilient shape. Living matter such as cells and tissues fit this feature, so man-made soft biomaterials play a key role in biocompatibility issues. Plasma engineering can transform solids and liquids into soft materials and is also able to functionalize them. In addition, one of the most widespread biomedical applications is sterilization. In the figure, we can see the bactericide effect of a hydrogen peroxide-cooled plasma over different infective plates, considerably reducing the growth of Aeromonas hydrophila bacterium. This effect has been reported for several bacteria and fungus. And finally, coronavirus disease, which emerges as a new global health emergency, made the medical community to focus its efforts on improving the safety and efficacy of vaccines and developing new therapeutics. Low-temperature plasma can play a vital role in both preventive and therapeutic strategies against COVID-19 because of its synergistic antimicrobial and immunomodulatory effects. Some approaches for SARS-CoV-2 inactivation by low-temperature plasmas were proposed, providing valuable knowledge in the fight against pandemics and diseases. Due to the looming climate crisis, the application of plasmas in the environmental field are gaining relevance. The removal of volatile organic compounds stands out, and it's frequently done through plasma catalysis. It has led to commercially available devices on the market. One of the critical steps of this process is the adsorption of the pollutant onto an adsorbing material prior to being oxidized at the surface by oxidizing species produced in gas phase by the plasma. Moreover, plasma treatment of toxic waste, such as asbestos products, hazardous industrial waste, or radioactive residues, is an essential issue in this field, since it takes part in the waste recycling. High temperatures reached in the plasma induce fast and complete pyrolysis of organic hazardous waste. Inorganic waste are melted and vitrified, resulting in the waste passivation and in its volume reduction. The most common plasma sources for this application are arc plasma torches and microwave torches. However, plasma technology is not only able to treat toxic waste, but also to revalorize them, obtaining valuable byproducts. In the figure of the slide, it is proposed a method to use biogas produced during agricultural activity as a raw material which would be decomposed by a microwave plasma at atmospheric pressure in hydrogen, syngas, and graphene. So, plasma technology can revalue biogas into a resource of high environmental interest. At the Laboratory of Innovation in Plasmas, we are currently working on this topic. And shifting topic, research on the application of plasma in agriculture emerged in the last 2 decades using cold plasmas operating at low pressure. These low-pressure plasmas are still successfully used for the treatment of various types of seeds to increase germination rates, but many of the applications nowadays rely on the atmospheric pressure plasmas as the electric barrier discharges. One of the most innovative applications of plasmas in this field is green nitrogen fixation for improving the efficiency of organic fertilizers. We can observe in the slide a sketch of a system that is suitable for this purpose. Powered locally by renewable sources, the air plasma reactor generates nitrogen dioxide that is absorbed by water or possibly waste livestock urine, creating nitric acid solution or ammonium nitrate from the acid reaction with ammonia. Related to this matter, plasmas are also being used to treat liquids, leading to the generation of plasma-activated water, which enables pathogen control and nitrogen fixation. Plasma treatments can also induce stress on plants, resulting in genetic and epigenetic changes and enhancing plant growth. In the picture, we can see 5-year-old plumeria from seeds without and with plasma irradiation. Once several applications of atmospheric pressure plasmas in different fields have been presented, it is needed to briefly talk about the perspective of this technology. Some innovative applications of plasma technology have been recently developed, and others are just now emerging. It should be highlighted cancer treatment, plasma propulsion, green energy generation, or the design of new materials, but there are much more. Plasma technology is suitable to represent a revolution in many areas, but certain challenges must be faced. For example, medical plasma application remain rather sporadic to date, and it is needed the establishment of standards and test protocols for plasma medicine. Furthermore, the most important challenge for cold plasmas to penetrate the food industry is to meet the required standards for the quality and safety of plasma-treated foods. In addition, some technical features of this technology should be improved, such as its scalability and energy efficiency, and deeper knowledge concerning plasma's fundamentals is still needed.
So, while presenting the fundamentals of plasma's atmospheric pressure, let's continue this lecture by understanding how plasma can functionalize material surfaces, pointing out different plasma sources for this purpose. After that, we will focus our attention into different surface characterization techniques, which will help us understanding the effect of atmospheric pressure plasma on the surface of the material. So let's begin by understanding the fundamentals of plasma surface treatment. Well, reactive species in plasma can interact with material surfaces. Consequently, plasma surface interaction can produce effects on surface of material such as activation, etching or coating, among others, that are possible to be reached or economically impractical through alternative methods. These effects alter surface properties such as surface energy, wettability, surface roughness, and many others. This fundamental idea is supported by some key points. Firstly, we should keep in mind that the plasma can interact or modify the surface of materials by different ways. For example, by adding or removing adsorbents, monolayers, involving chemical reaction with the surface, changing the physical or chemical state of the superficial monolayers of a material, or producing the deposition or adhesion of nanoparticles or thin films on the surface. Moreover, plasma functionalization is a surface treatment in the material which does not affect material bulk and then not affecting bulk properties. On the other hand, we could establish different plasma surface treatment. The first classification is based on the nature of the material treated. For example, heat-sensitive materials such as polymers, fibers, or fabrics, and less heat-dependent materials such as metals. The second one is focused on the surface property altered. As an example, let's mention the improving of wettability properties. The last and third classification is related to the type of plasma exposition, which could be either active or passive plasma exposure. Treatment by active exposure occurs when the material is necessary to generate the plasma itself, for example, being an electrode. Or treatment by passive exposure, which occurs when plasma active species bombard the surface of a material. Up to this moment, we have not think about the plasma process or plasma agents responsible for plasma surface treatment, so let's dive in it. Among any effect of the working gas, plasma processing effects are due to the action of active species generated by or inside the plasma. These species result from inelastic electron-neutral collisions by an electron population with a characteristic electrokinetic energy ranging from 2 to 10 electron volts. These relatively high energies provide enough energetic electrons to produce such inelastic processes as ionization, excitation, or molecular dissociation when they collide with the plasma constituents. Which are these plasma species? Well, those are photons, neutrons, or charged particles. Let's start by photons. Photons are available from the plasma over a broad spectrum of wavelength in the electromagnetic one. These photons are produced by the de-excitation of plasma species into lower energy states. How do photons interact with material surface depending on their energy? Well, infrared photons have the same general effect of a hot wall or ordinary chemical reactions, where a higher energy photons in the visible electromagnetic spectrum can break some molecular bonds and excite atoms, and even higher energy photons such as ultraviolet photons can ionize and excite atoms or break molecular bonds to form smaller molecular fragments. Therefore, the interaction of energetic photons can produce on surfaces the formation of free radicals or monomers, changes in the molecular state, or the accumulation of charge on the surface. Through electron-neutral collisions and chemical reaction in the plasma can produce several kinds of energetic, active, neutral species capable of interacting strongly with the surface. These neutral species include reactive atoms. For example, reactivity is a measure of how easily an element will combine with others to form compounds, for example, on a surface. As an example, let's mention alkyl metals. Highly chemical reactive atomic species such as hydrogen, oxygen, and so on, where the number of electrons in the outermost shell of this atom determines its reactivity or tendency to form chemical bonds with other atoms. Another neutral species are monomers, which form polymeric chains on surface which they can interact with. Relatively light molecular fragments or heavy molecular fragments are also named as neutrals, which can form complex compounds on surfaces and or promote branching or cross-linking on molecules near to the surface. Excited atomic or molecular state, in which excitation of orbital electrons makes a species more chemically reactive, that is normal as the ground state. Free radicals, molecular fragments generated in the plasma with at least 1 ampere electron are other examples of neutral species. All such as reactive species may interact strongly with surfaces. The charged particles available from a plasma include electrons and ions, both positive and negative respectively. Electrons are produced in the plasma by electron-neutral impact ionization, which typically have kinetic temperature of 1 to 10 electron volts. Positive ions are produced by ionization and charge exchange. Negative ions are produced in the significant number in atmospheric pressure plasma by attachment of electrons. Molecular ions can also be produced and may include such charged molecular fragments as OH, which may undergo strong chemical reactions in the plasma or on the surface. Reaction types between active species and the surface property of sheath through plasma processing mainly depend on the used gas and plasma chemistry, for example, gas type and gas composition, and of course on the surface material which is being treated. As it can be observed in this slide, we can consider 4 different types of plasma surface interaction, which can be classified into different surface modification groups. The first one is etching or cleaning. During etching or cleaning, the surface is exposed to positive ions, UV radiation, and reactive neutrals. Volatile products are formed on the surface and are removed, resulting in clean, decontaminated, or sterilized surface. Plasma etching is a high-precision materials removal technique employed, for example, in semiconductor manufacturing and other industries, where plasma containing reactive ions or radicals chemically interacts with a material's surface. This controlled interaction facilitates the removal of specific layers or patterns from the substrate, allowing for the creation of intricate structure with fine detail and accuracy in the production of microelectronics and other nanoscale devices. In the case of plasma activation, plasma species react with the surface while retaining the original structure of the underlying layers. Both substitution and addition reactions are possible while free radicals are formed on the surface. Surfaces exposed to plasma-active species results in changes in chemical structure of surface molecules. When active species interact with the workpiece material itself, it means the substrate, the surface property of the workpiece can change. A new compound can be formed or molecular fragment can be attached to a polymeric or hydrocarbon-based substrate material. As an example of the importance of surface chemical reaction, let's consider 3 active species: the carbonyl group, the hydroxyl group, and the carboxyl group. The chemical attachment of these groups to hydrocarbons or polymers is not to affect such surface energy-dependent properties as wettability, wickability, and printability of polymeric materials. The deposition of plasma-generated nanoparticles as spacers of the surfaces in a single process step is another promising functionality, for example, to modify roughness of a surface. In the case of nanoparticles formation, precursors materials are introduced into the plasma, where they undergo chemical reaction and physical transformations. The energetic conditions within the plasma facilitate the dissociation and recombination of atoms, leading to the creation of nanoscale particles. The versatility of plasma processing allows for precise and control over the nanoparticle size, morphology, and composition by adjusting simple parameters such as gas composition, pressure, and power. Another functionalization could be considered film deposition. Film deposition at coating is achieved by so-called plasma-enhanced chemical vapor deposition. In this case, this plasma contains reactive species capable of reacting with each other on top of the substrate to form a thin film. The polymerization may happen in the gas phase by the injection of precursor monomer and subsequent deposition on the substrate, or by free radicals which are formed on the surface and then react with gaseous radicals. Among other processes, it includes plasma polymerization, which is a widely used deposition method in which monomers supplied to or produced within the deposition chamber by plasma chemical reaction polymerize on contact with the workpiece to build up a polymeric coating and epitaxy, in which atoms of a crystalline material are supplied to a reaction chamber or produced by chemical reactions in the immediate vicinity of the workpiece. These atoms or precursors deposit on the surface to produce successive monolayers of a crystalline material. Recently, the functionalization of surfaces by the deposition of nanocomposites on the surface is being explored. The formation of nanocomposites through plasma processing involves the integration of nanoparticles in a matrix material under the influence of high-energy plasma environment. In this method, precursor materials, including the matrix and nanoparticle components, are subjected to the plasma, leading to surface modifications and functionalization, and the creation of well-dispersed nanocomposite structure. The energetic interaction with the plasma facilitates the bonding and incorporation of nanoparticles into the matrix, offering enhanced control over the composite's properties. They are attracting the attention of the scientific community involved in material science and technology as they show multifunctional properties. Effective surface functionalization demands attention to key needs. Large area functionalization is vital for diverse industrial applications, while high material throughput ensures efficient processing. A smooth and uniform treatment is crucial for product quality, whereas reliability and stability are both essential for continuous production, minimizing downtime. Prioritizing low gas consumption and using cost-effective recycling aligned with sustainability and eco-friendly practices. Addressing these requirements collectively boosts the efficacy and practicality of surface functionalization across different industrial settings. Which are the plasma process approaches for this purpose? On the one hand, direct plasma processing, where the active species are created directly near the substrate, with the substrate placed in between the electrodes of a system. One common example of this approach is the use of the electric barrier discharge. On the other hand, indirect plasma functionalization, where the active species are created remotely in the plasma and pushed onto the surface. This second approach is also commonly known as atmospheric pressure plasma jet or post-discharge deposition process, which are suitable for complex 3D substrate of any shape and thickness, and as there is not electrode spatial confinement. Next, we will really remember both the electric barrier discharge and post-discharge processing of surface for different surface functionalization. As it has been discussed previously in this lecture, and making a very rough generalization of the system, we could mention that atmospheric pressure, the electric barrier discharge, are generated in the space between two electrodes, each of which is covered by an isolated dielectric coating. A substrate can be placed in between both electrodes, and thin films, nanoparticle or nanocomposite can be deposited on it. Depending on the plasma parameters and precursor nature, new material properties can be tailored. In this lecture, let's focus our attention on its use for the synthesis of thin films such as diamond-like carbon, nanoparticles such as titanium dioxide nanoparticles, or nanocomposites. Let's continue with the use of post-discharges. Surface wave discharges are a special kind of microwave discharges, typically contained into small diameter dielectric tubes. If nitrogen is introduced in an argon discharge under certain experimental conditions, a specific and important change is observed upon nitrogen introduction: the appearance of a diffuse zone after the direct column known as remote plasma, afterglow, or pore discharge. In the discharge, ions, electrons, excited species, and neutral can be found. However, in the afterglow region, only those excited states which need more time to de-excitate, which are also called long-life excited state or metastable, can be found together with argon atoms and nitrogen molecules. In this weakly ionized or neutral medium, which cannot be considered a plasma region itself, reaction pathways are more restricted than in the discharge, where electrons play a fundamental role in the internal kinetic. Another interesting feature of these afterglows is that the macroscopic temperature of the gas dramatically decreases along the post-discharge, even reaching room temperature. All these features make the use of microwave afterglows very interesting for the treatment of thermosensitive material surfaces such as biological ones, without ion bombardment or etching of the surface. In this lecture, we will discuss the effect of argon-nitrogen post-discharges on the cleaning and activation of aluminum surfaces.
In this section, we will introduce some of the most widely used techniques for surface characterization. But first of all, we must wonder, what are the most relevant properties and therefore a priority in our analysis? One of the most important properties is the chemical composition of the surface, what elements compose it and how they are distributed. We may also be interested in characterizing other properties, such as surface roughness or wettability. In the case of thin films, it's essential to measure the degree of coverage as well as the thickness of the film. Regarding the deposit of nanoparticles, we need to know their size and their distribution around the surface. In order to study these properties, we can make use of different characterization techniques, among which we highlight X-ray photoelectron spectroscopy, scanning electron microscopy, atomic force microscopy, and finally, water contact angle measurements and surface free energy calculations. X-ray photoelectron spectroscopy, or XPS, is a surface-sensitive analytical technique in which the material is irradiated with X-rays and the kinetic energy of the emitted electrons is analyzed. It's a widely used technique due to the diversity of information it can provide. With XPS, for example, we can identify all the elements present in the sample, except hydrogen and helium. We can also obtain information about their chemical state. Regarding compositional analysis, we can measure the surface composition as well as the spatial distribution of the elements. Also, if the surface is covered by a thin film, we can measure its thickness and homogeneity. On the other hand, the interpretation of results is not straightforward for a novice user. So it's quite important to understand the basics and to check specialized sources to avoid the misinterpretation of the spectra. If we talk about a microscope, the Rayleigh criterion sets the limit of resolution in a diffraction limited system. This limit, which defines the smallest distance that can be resolved, depends on the wavelength of the source. When we deal with electrons, their wavelength decreases with energy, so that if we use electrons at high energies, we can resolve elements on a spatial scale which is unreachable in an optical microscope. Although this is the main idea behind the development of electron microscopes, their usefulness goes beyond that. When an electron beam impinges on a sample, it interacts with it, generating different types of signals. In an electron microscope, we have different detectors that collect these signals and transform them into usable information. Specifically, in a scanning electron microscope, we can use secondary electrons to obtain topographic contrast, while with backscatter electrons, we can measure compositional contrast. Furthermore, we can carry out localized compositional analysis using energy dispersive X-ray spectroscopy. In an atomic force microscope, a sharp tip scans the surface of a sample very closely, tracking the forces of the interaction between the tip and the sample by measuring the displacement of the reflection of a laser beam on the cantilever containing the tip. It provides information on size, depth, thickness, roughness, adhesion, or viscoelasticity, among others. Among its advantages is a non-destructive technique that can achieve high spatial resolution. It also requires minimal sample preparation, but on the other hand, the analysis of large areas may require long times, limiting its application. Finally, another very common type of measurement is contact angle and free energy. The contact angle is defined as the angle made by the intersection of the liquid-solid interface and the liquid-air interface. A high contact angle indicates a low chemical affinity or a low degree of wetting. On the other side, a low contact angle refers to a high chemical affinity and a high or even sometimes a complete degree of wetting. We are often interested in water contact angle measurements. These kind of measurements can be performed after taking different photographs of droplets deposited on the surface. When the water contact angle is greater than 90 degrees, we say that the surface is hydrophobic, while if the angle is less than 90 degrees, it has a hydrophilic behavior. A parameter which is related with the contact angle is the surface free energy. Interactions between solids and liquids are important in many processes, as they determine the adhesion between the two phases. While the measurement of the contact angle on its own indicates the wetting of the solid by a particular liquid, the surface free energy represents the quantitative measure of the intermolecular force at the surface, which is independent of the liquid used. So, by knowing the surface free energy of the solid, one can predict the behavior of any liquid on the surface. However, surface free energy cannot be directly measured. So, to calculate it, measurements with at least two different proof liquids are required. According to the Owens-Wendt model, if we measure the contact angle of the liquids with the solid, and the polar and the dispersive components of the surface free energy of the surface are known, then the polar and the dispersive components of the solid can be calculated. Let us now see how to apply these techniques by means of different examples covering all the applications of plasmas on surface seen before. We will focus on the application of techniques to solve different questions. So, for a detailed description of the experimental setups, please refer to the references included in the slides. In this first work, the aim is to analyze the effect of an argon-methane dielectric barrier discharge plasma on a glass surface. For this purpose, first, the water contact angle was measured as a function of the percentage of methane introduced into the gas mixture. It was found that the introduction of methane induced a change in the wettability of the samples. For methane concentrations about 0.25%, the surface showed a hydrophobic behavior, which is consistent with a decrease in surface free energy. We wanted to understand the phenomenon causing this behavior. According to the bibliography, the hydrophobicity could be due to changes generated either in the surface roughness or composition. The surface morphology was therefore analyzed by atomic force microscopy. Here we can see two-dimensional AFM images obtained before and after treatments. From these maps, the mean square roughness can be calculated, obtaining a similar value for all the different cases. This indicates that the surface topography is not a contributing factor. So, the next step, therefore, was to check for compositional changes after plasma treatment, for which XPS was used. According to the XPS spectrum, the surface of the reference sample consists mainly of oxygen, carbon, and silicon. However, the sample treated with an argon-methane plasma shows a spectrum dominated by the carbon peak, while no silicon peaks are detected. This suggests that the formation of a thin carbon layer on the surface occurs after the plasma treatment. To extract useful information about this layer, the carbon line shape was fitted with appropriate functions. The different peak shapes in the treated and untreated samples revealed different chemical bonding environments. The best fit of the carbon peak for the treated sample only requires two components. The first one, at the lower binding energy, is attributed to the sp2 carbon atoms. Another peak at larger energy, which is attributed to the sp3 carbon atoms. This suggests that a diamond-like carbon thin film has been deposited. Diamond-like carbon is a class of amorphous carbon material that displays some of the typical properties of diamond. This material can be applied as a coating layer to other materials which could, this way, benefit from such properties. In these works, the use of a post-discharge of argon and argon-nitrogen microwave plasmas for cleaning and activating the surface of metallic commercial aluminum has been studied. Measurements of the water contact angle shows that increasing nitrogen concentration leads to an increase of the hydrophilicity of the surface. Furthermore, the post-discharge induces an increase of surface free energy, reaching the standard value, which implies that the aluminum surface is therefore clean for future processes. One might wonder if the temperature is responsible for surface modifications. To check this hypothesis, the aluminum surface was exposed to external heating. The information obtained after heating is represented in the figure by an horizontal green bar. As it can be seen, there are only small differences in comparison with the untreated samples. Therefore, we can conclude that temperature is not responsible for the surface modification, so it has to be related to chemical modifications. To check this, the samples were analyzed using XPS. According to XPS, untreated surface is composed of aluminum, oxygen, carbon, and fluor. The intense oxygen signal suggests the presence of an oxidized aluminum layer below an external hydrocarbon layer, whereas fluor and carbon are related to the processing of aluminum foils. By observing the individual signals, it can be seen that the post-discharge treatment generates a decrease in carbon and an increase in oxygen and aluminum. This suggests that this external hydrocarbon layer may be being removed with the treatment. However, this effect, although to a lower extent, is also seen when the sample is heated, so it cannot be the only factor causing the change in wettability. For the sake of clarity, a fitting of the aluminum and oxygen peaks has been made, allowing a more detailed study of the chemical environment. Although no considerable differences were seen in the aluminum signal, this was not the case for the oxygen. Experimental oxygen signal can be deconvoluted into three main components. The first one, which is related to the presence of water in the surface, the second one due to the presence of hydrophilic hydroxide groups, and the third one attributed to oxide groups in aluminum oxide. From the spectra, it can be observed that, as compared to the heating processing, the post-discharge treatment removes the water absorbed in the surface, whereas increases the contribution of hydroxide groups. Therefore, we can conclude that both the removal of the hydrocarbon layer and the incorporation of hydroxide groups in the surface are responsible for the cleaning of the surface, and this is only due to the plasma treatment. Finally, in this last work, the synthesis of titanium dioxide nanoparticles, carbon nanocomposites by DBD is discussed. In my opinion, the results found here are particularly interesting. Why? Well, as we will see, from the same system and precursors, and depending on the parameters used, we can obtain either a thin layer of carbon, a coating of titanium nanoparticles, or a nanocomposite formed by the nanoparticles inside a carbon matrix. For this purpose, a solution of titanium dioxide nanoparticles was prepared in isopropanol. This solution was then introduced using either a nebulizer or an atomizer into the chamber of a dielectric barrier discharge reactor with a well-controlled atmosphere. Scanning electron microscopy is a very useful tool to characterize the structures obtained for each case. According to the images in the lower left corner, it can be seen that by changing the nitrogen flow, clusters of nanoparticles with different appearance are obtained. Although their size is similar, the nanoparticles obtained under lower fluxes are more isolated. On the right, we can see the effect of changing the DVD frequency. By using low frequency, we obtain clusters of nanoparticles like the ones mentioned just before. However, when we switch to a high DVD frequency, instead of nanoparticles, a thin film coating is obtained. In these images, instead of a frontal view, we are looking at a cross-section obtained after a transversal cut of the sample. Thus, in a simple way, we can not only see the morphology of the sample, but also the thickness of the layer of the deposited material. To conclude this section, I'd like to remark that in order to properly characterize a material, it's necessary to combine different techniques as they complement each other. The use of a single technique may imply the risk to misinterpret the results.
Welcome to the third block devoted to the synthesis of graphene through atmospheric microwave plasma. The block is organized in two sections. In the first one, we briefly introduce the basics of graphene material, the experimental setup, and the characterization of the process and the material. In the second section, we describe our modeling approach to solve and simulate the whole plasma process, including electromagnetics, fluid flow, energy, and particle growth. Now, let's start with the introduction of graphene, a perfect two-dimensional material formed by carbon atoms with sp2 hybridization. This structure tends to evolve into other types such as graphite, fullerenes, and carbon nanotubes. Therefore, graphene is considered as the basic structure of all graphitic materials known to date. Also, graphene has the ability to combine with other elements. For example, doped graphene refers to the introduction of atomic elements into the carbon structure. Functionalized graphene refers to the modification of the carbon surface with functional molecules or polymers. And the combination with two or more materials, such as carbon with polymers or metals, or metal organic frameworks, or carbon nanotubes, are known as graphene nanocomposites. As a result of the atomic and electronic structure, graphene and graphene-based materials have extraordinary and enhanced properties such as high hardness and flexibility, high electrical and thermal conductivity, optical transparency, etc. And consequently, their applications are unlimited, including chemical sensors, electrodes for fuel cells, weather and gas purification membranes, etc. Now, let's talk about the current industrial methods to produce graphene. These include two main techniques, top-down and bottom-up. Chemical vapor deposition is a bottom-up technique producing one single layer of graphene in a process involving the use of a catalyst and the decomposition of a carbon precursor at high temperature. The quality of the produced material is the best among the graphenic materials. However, the use of a metallic substrate makes this technique quite expensive. On the other hand, the liquid phase exfoliation is a top-down technique using graphite as a raw material and producing high quantities of multi-layer graphene structures. This technique is more affordable than the CVD1. However, the material presents a high presence of defects and implies an environmental challenge because of the use of solvents in the process. We should ask us why plasma can be used in graphene production. As mentioned in block 1, atmospheric microwave plasmas can break down any molecule because of the presence of high density of electrons. Those electrons can break and decompose any input into atoms and radicals that recombine at the plasma exit, forming solid and gaseous products. The plasma system is usually powered below 1 kilowatt at atmospheric pressure. These conditions produce two different temperatures, one for the electrons and the other for the gas, being higher the temperature of the electrons. Let's now take a look to the whole experimental setup at the Laboratory of Innovation in Plasmas. This is composed of the Tiago torch itself, connected to a microwave power generator, to a gas flow system, and to the characterization tools, which are one, the optical emission spectrometer, composed of a monochromator and an optical fiber that collects the radiation emitted by the plasma just above the tip of the torch, and the mass spectrometer, which is connected to a lateral outlet of the reactor for the monitoring of the exhausting gases. Specifically for the graphene synthesis, argon is injected into the Tiago and ionized through the microwaves. Separately, ethanol is heated up with a controlled evaporator mixer before being injected into the process. Once the plasma is stable, ethanol is injected. Now, with this slide, let's visualize the decomposition of ethanol in the plasma system with the operating conditions described in the previous slide. As it can be seen in the pictures, the flame size increases as the flow rate increases. The color and morphology of the plasma are already indicating the influence of the operating conditions. Now, we will continue the analysis of this effect on the plasma species and kinetics, as well as the product's formation. With this slide, let's understand the effect of ethanol flow rate and the plasma kinetics by the optical emission spectroscopy technique. As it can be seen, the concentration of nitrogen and oxygen from the surrounding atmosphere affects the formation of plasma species at either low or high ethanol flows. Carbon-nitrogen formation is favored to carbon-2, whereas increasing both parameters is translated to the emission of carbon-2 species, which are related to the graphene formation itself. In both cases, ethanol is completely decomposed and hydrogen is formed as a byproduct. However, we observe when using larger ethanol and argon flows, the process is more effective. Under these conditions, solid material, the graphene actually, is formed in the reactor. Hydrogen is the main byproduct, and more important, there is the absence of polyaromatics or greenhouse gases. This is therefore a confirmation that our process is a green process. Now, the gas temperature is also calculated through the optical emission spectroscopy analysis. On the other hand, the presence of acetylene and other gases are confirmed through mass spectroscopy. You can see on the plots the carbon and acetylene species formation during high and low air influence. Here we represent as the A and B routes, respectively. And as a conclusion of this process characterization technique, the B route with gas temperatures higher than 4,500 Kelvin is more effective for the graphene synthesis with the formation of hydrogen as a byproduct and without the formation of CO2, and therefore this ensures a clean process. Now, in addition to the plasma process characterization, we are going to talk about the product, the material characterization with different techniques, such as Raman spectroscopy, high-resolution transmission electronic microscopy, X-ray photoelectron spectroscopy, XPS, and thermogravimetric analysis, TGA. These are the most common techniques used to characterize graphene and to identify the presence of functional groups and morphological modifications on the graphene surface. Let's start with the Raman spectroscopy, which is a common technique to determine the characteristics of graphene, such as if it's a monolayer, few layer, or if it's a graphene oxide. This is a non-destructive method using a chromatic excitation laser to verify the structure of the material. In Raman spectroscopy for graphene, there are three main response peaks to observe: the D, the G, and the 2D. The G band appearing at 1500 AD level corresponds to the plane configuration of carbon atoms bonded with sp2 hybridization. This location of G peaks discards the presence of graphene oxide, which is slightly upshift to 1594. Now, the D peak at 1352 can be related to defects, which refers the presence of sp3 carbons in the basal carbon plane, such as disordered graphene and to graphene oxide. And finally, the width and the height of the 2D peak can relate to the number of layers. This Raman technique is very used in industry and laboratory to identify the graphene characteristics through the Raman ratios D over G and 2D over G. We can see in this slide our results show a small value of DG ratio combined with a 2D G ratio higher or equal than 1, which indicates low defects and few number of layers as indicators of a good quality of graphene, which is the case of the graphene produced at the Laboratory of Innovation in Plasmas. Now let's talk about the morphology of the material with the high-resolution transmission electron microscopy, which is identical to transmission electron microscopy imaging, except that the magnifications used are high enough to easily see the lattice spacing of inorganic materials, typically of the order of several angstroms. Here our HRTEM images show that the produced graphene consists of few layered sheets of 2, 3, and 7 layers without the presence of any other particles such as carbon nanotubes or graphitic particles. This indicates the selectivity of our process in the synthesis of pure graphene and in relation to the formation of other carbon structures. Now, in this slide, we can observe the Raman spectrum and TEM analysis of the graphene produced by plasma by graphite exfoliation versus the graphene produced from plasma. Graphene from exfoliation presents higher number of defects and more layers. The morphology is also very different. The graphene from plasma produces flakes with a highly crystalline turbostratic structure and crumpled morphology. This morphology is thought to be important for electron transport and therefore energy storage. In this slide, we can observe the XPS analysis, which was explained in the second block, as an analytical technique to analyze the element composition of the sample. For our graphene produced by plasma with the Tiago torch, we can observe the presence of carbon atoms as the majority elements and a very small amount of oxygen that can be mainly attributed to the influence of atmospheric oxygen during the extraction of graphene from the reactor. And the convolution of carbon-1 S peak allows to carry out a detailed analysis of the types of carbon present on the surface of graphene, confirming a maximum percentage of sp2 hybrids and low defects in graphene corresponding to sp3. And finally, the TGA is a complementary technique for the measurement of thermal stability of materials, homogeneity and purity. This technique can help us to confirm the elemental composition through the burning temperature of a species. Regarding TGA is a useful tool to determine the functionalized graphene or functionalized graphene oxide weight loss under aggressive temperatures. Here we can see the decrease of mass in certain temperature range, which can be associated to the uptake of moisture, oxygenated groups, and nitrogen compounds. Our synthesized graphene was analyzed under aerobic conditions of 50 milliliters per minute and a heating rate of 5 Celsius per minute. We conclude that only one oxidation temperature around 550 Celsius shows that the material is free of amorphous carbon at 300 and 400 Celsius. And this is therefore an indication of the high quality of our graphene. At this point, we have shown microwave plasma technology working at atmospheric pressure as an option to produce defect-free fuel layer graphene with high yield, hydrogen as a main gaseous byproduct. During the ethanol decomposition, the process is cost-effective and, more important, eco-friendly because greenhouses are not formed. This approach is a first step for the implementation in the industry because it can operate under different experimental conditions, being scalable and versatile. For such purpose, the next step is to study how microwave plasma technology at atmospheric pressure can be optimized to produce high quantities of both graphene and hydrogen, reducing the costs while keeping the quality and characteristics of the byproducts. And an important tool to understand and optimize the process is our next section devoted to the numerical simulation of the process.
The last part of the course is devoted to the numerical modeling of our system. Let's revise the motivation for a numerical modeling of our system. First, in our system there are many reactions involved at the same time: a gas flow, the plasma evolution, the precursor dissociation, particle and heat transport, nucleation, electromagnetic field evolution, etc. To solve the whole process, it is necessary to separate all these phenomena and their effects, which result in a better understanding of each particular reaction. As a consequence of this analysis, it is possible to identify the key parameters of the whole process of the graphene production and the regimes of operation. Along the modeling process, it is necessary a simplification of these reactions and a complete standardization of the experiment. This fact increases the reproducibility of the phenomena and allows a better comparison with similar but different experiments in other laboratories. These activities will help us to validate the processes leading to the development of a synthetic diagnostic tool, which also helps to significantly reduce the associated cost of new experiments. In particular, after the identification of these key parameters, we can use them to optimize or improve the reactor to facilitate the formation of graphene. This step is crucial to scaling up the process to a more competitive industrial level. Finally, the possibility of a complete analysis, including theory, experiments, and numerical validation, results in a better control of the experiments and a significant increase of the laboratory independence. Among all the reactions or phenomena involved in the process, the system is governed by the fluid dynamics. It is behind the injection of the gas flow, the evolution of the argon plasma, the dynamics of the dissociated components, and the air inside of the reactor. These fluids have an important boundary conditions in a fixed geometry, and best approach to model these subsystems is the computational fluid dynamics, also known as CFD. Even more, during the last decades, the CFD modeling has advanced, adopting modern numerical techniques for the reduction of the computational cost. Nowadays, we can run a CFD model in our mobile phone or personal laptop. In our case, we are going to use ANSYS Fluent, which is a platform for a quick immersion in the CFD modeling because it includes several validated routines for mesh construction, solver of physical or chemical models, and it also offers a free but limited version for students. ANSYS Fluent uses a finite volume method to divide domains into controlled volumes with constant parameters that evolves following a discrete transport equation. It is also a multi-physics platform that includes many models for turbulence, radiation, thermodynamics, electromagnetics, and specific properties of materials. At the same time, this software offers the flexibility to include new models in C language. In our case, this will be crucial or fundamental for the plasma and nucleation modeling. Let's revise the assumptions and limitations of our plasma modeling. The plasma has two species with different and independent temperatures, Te for the electrons and Tg for the gas. Electrons are much lighter than the heavy gas particles, and during the heating of the plasma, they reach higher velocities, or in other words, the electron population has higher temperature. We will only consider the main ionization recombination reaction in our modeling. In this reaction, argon atoms lose 1 electron and they become ionized with one single positive charge. Another assumption is that the injected flow is continuous and turbulent, like in a flame. Also, even when the electrons and ions are independent populations, the plasma is quasi-neutral, which means that it has the same number of ions and electrons and is electrically neutral. Finally, the problem is an axisymmetric problem, or we are going to consider cylindrical symmetry. Basically, it's a 2D problem. Here, we can see a summary of the complete model. The model is constituted by 3 important subsets of equations that are coupled and solved inside a Thiago reactor. In the first step, we have the electromagnetic effects that are considered through the Maxwell equation in green. Remember that our plasma is constituted by a population of electrons and positively ionized argon atoms and neutral atoms that will interact between each other. In orange, we also have the main core of the 2-temperature plasma model, which is the heat and particle transport of each species, including the mass, momentum, and energy conservation, and the turbulent transport model that is provided by the ANSYS Fluent software. Finally, in blue, we can observe the graphene formation, including the expressions for the nucleation, condensation, and coagulation or growth of structures on the reactor walls. Now we present a selection of the most relevant diagnostics implemented in our model to illustrate some of the possible analysis. In this case, for example, we can observe the electron on the left and the ion on the center temperature maps. This diagnostic, combined with the density map, right picture, is particularly interesting to determine the regions with ideal conditions for the nucleation. In particular, in these pictures, we can see that the initial injection of the gas flowing through the torch with the corresponding temperature, as well as the density of electrons and their corresponding temperature. Now, in this slide, we can observe the velocity maps that are also very interesting for our purposes. These maps illustrate the velocity with colored arrows or vectors for all the points of the reactor. The color of the vectors allude to the magnitude of the velocity. In these maps, there are a lot of information, but also at first sight, we can identify the passing regions where particles have higher velocity and trapping regions where the particles have lower velocity. If we make a zoom in the blue regions close to the walls, we can observe that the recirculation process that can be related to a higher residence time and therefore to have an impact in the formation and growth of the graphene. In any case, for a better understanding of the recirculation patterns, we can plot the stream function or flow. Here we have 3 situations with different gas injections. We can observe that the recirculation patterns appear in the 3 situations, but these patterns are stronger with a higher injection of the gas. Even more, the recirculation flows also grow and reach the top region of the reactor with higher injection of gas, increasing the possibility of nucleation on the upper walls of the reactor. In terms of physics, we can also observe the turbulent viscosity ratio. We should keep in mind that turbulence is behind the recirculation patterns, otherwise the flows will be laminar, and is increased with the gas flow, as we expected from the previous slide. Nevertheless, if we compare these patterns with the recirculation ones, we observe that are not the same. Even more, the turbulent patterns are significantly different in terms of the flow injected. Finally, we can also plot the residence time patterns. It is interesting to compare them with the recirculation patterns because obviously particles trapped at the recirculation fluxes tend to stay longer in the volume of control. As we increase the flow injected, the residence times is reduced in the top of the reactor because of the particles trapped at recirculations. And in this region of the reactor, the velocity is high because our returning points. Along the presentation, we have studied and modeled many reactions present in the reactor. But we must remember that in the end, the main objective of the whole process is the production of graphene. In that sense, after the identification of the key parameters of the process, we can use our numerical tool to maximize the production of the material. This stage is crucial to scale the production to a competitive industrial level, but usually the optimization or improvement of the process is arduous, long, and expensive. We must favor the regimes and parameters that increase the production of the material, but at the same time keeping the quality of the final products and controlling the cost of production. Here we have the usual experimental and numerical procedure to evaluate a change in our reactor. These procedures evaluate a single parameter, and ideally it is better to test every single modification isolated from the rest to avoid possible interaction or contamination between the different modifications or effects. We observed that the initial stages, identification of key parameters and the design of a new reactor, are the same in both schemes. But after the design, if a numerical model is available, it can be used as a synthetic diagnostic to test thousands of configurations, changes, and improvements in a very reduced amount of time and with an almost zero cost, only the electricity of the computer. Then, after the study, we can create the final prototype, only a single final prototype, to validate and control the graphene quality. Meanwhile, in the experimental procedure, it is necessary to build many new prototypes of the reactor with those improvements or additional parts or changes in the structure in the absence of a numerical model. Those prototypes are expensive and require a lot of design and manufacture. In this lecture, the Innovation in Plasma team shared how atmospheric pressure plasma can be a game changer in material science technology. We started with a comprehensive overview which includes the basic atmospheric pressure plasma technology, covering plasma fundamentals, different plasma sources, and its wide-ranging application. Then we focused on how this groundbreaking technology can be used for the treatment and functionalization of surface and the synthesis of graphene. We use different techniques to study these functional materials and to optimize the outcomes from the graphene generation process. The lecture culminated with an exploration of the plasma modeling, a crucial aspect that empowers both experimental and theoretical control of the high-quality graphene synthesis process. By integrating this model approach, we illustrated how it contributes to a comprehensive understanding and refinement of the synthesis process, paving the way for advancement in atmospheric pressure plasma technology. Thank you very much for your interest and attention. It has been a pleasure for us to give this lecture.